In this section, we're going to be looking at limits and infinity. This seemingly doesn't have to do a lot with the material that we've been going over in the last few sections, but we're going to be using this material in the next couple heavily. If you are not familiar with limits, if it's been a while, you may want to review Chapter 1 and go over all those limit rules, as we will be using those throughout the entire section. The difference in what we're going to be looking at now and what we did in Chapter 1 is going to be that instead of x approaching some finite number, we're going to let x get very, very large or get very, very small, approaching infinity or negative infinity. If we're thinking about the definition of the limit, we have, if the limit as x approaches infinity of f of x equals L, we're saying that if x is large enough, we can get our function value as close to that value L as we would like. We say that the function approaches L as x approaches infinity. So let's look at three examples right now, looking at the limit as x approaches infinity. Example 1a, we look at the limit as x approaches infinity of x cubed. So we're going to say as x approaches infinity, we're going to let x get bigger and bigger and bigger, going further along the x-axis. If we look at the corresponding y values, the function values, those y values just get bigger. We can say that y approaches infinity. That means that this limit is infinite. Another way to do that, a little more algebraically, is we could say that the limit as x approaches infinity of x cubed, we can use our limit rule from Chapter 1 that the first thing we should do with limits is plug in infinity into our function. Now we can't correctly plug in infinity. It doesn't really make sense to plug in that number, so we're going to put this in quotation marks. But we can think about this as quotation infinity cubed, and if you cube a really, really big number, you get a really, really big number out. So even though we're not really allowed to plug in infinity, we can think about plugging in infinity to understand what's going to happen. So that's the first example right there, example 1a. Let's look at example 1b now. We're going to do the same thing. As x approaches infinity, we're going to let x get bigger and bigger and bigger going along the x-axis. What happens to this corresponding y values? In this case, it definitely doesn't seem like the y values get really, really big or really, really small going to infinity or negative infinity. They seem to get closer and closer to 0. So we're just going to put right now, y gets closer and closer to 0, but we're going to put a question mark because we're not really sure if it goes all the way to 0 or maybe it goes somewhere close to 0. And it is going to matter what exact value it does approach. We can see that at least it's not going to be going to infinity or negative infinity. We can also think about algebraically what would happen if I plug in infinity here. So if I have the limit of x over 3x minus 1, plugging in infinity, we have infinity over 3 times infinity minus 1, and this will give us infinity over infinity, which we've talked about before, is an indeterminate form. So there is an issue here with this limit by plugging in that value. And this is why we can't really figure out exactly what value it's approaching, because this infinity over infinity means that I can't determine what the answer is. It means that I have to do something else. We'll examine this one a little bit more on the next page. This third example, if we let x get closer and closer to infinity, we're letting x get really, really big, what happens to the corresponding y values? Well, sine is just going to keep on going up and down as we go out, which means that the y values are going to be going back and forth from 1 and negative 1 forever. So do we say that y approaches 1? Do we say y approaches negative 1? Do we say y approaches the middle of those, 0? And the idea is, we've talked about this in chapter 1, that the limit must be unique. So therefore, since we don't know if it's 1 or -1 or 0 or something in between, then this limit does not exist. It has to approach one value. We're going to see in example 1b that even though we don't know what value it approaches, it is going to approach just one value. All right, let's take a look at 1b again on the next page. And this time we're going to look at the table of values to help us out. We're going to plug in bigger and bigger x values. And see what happens to the corresponding function values. And when we do this, we see that the function values are getting closer and closer to 0.333 or 1/3. These are approaching 1/3. And we can see in the picture, I drew a little more detail here, that we have this dotted line here. This is a horizontal asymptote. That the function is approaching as x gets larger. Now, in both of these cases, using just the graph and using just the table, here's a note here, using just the graph or just the table is not enough. It's a good idea to kind of see what's going on, but we need to take care of this algebraically, which we will see in just a little bit. We always have the option of doing a table, but after the first few examples we did at the beginning of the semester, we can see that this is really an inefficient way of dealing with limits. All right, we can also look at limits as x approaches negative infinity, which we're going to do on the next page. So instead of looking at infinity, now we're going to approach the other direction, looking at negative infinity. So we can say, as x approaches negative infinity, what happens to the corresponding y values? In that first example, x cubed, we can see that the y values approach negative infinity. And again, we can think about this algebraically by, quote unquote, plugging in negative infinity. And the difference here, and why this is nice to do sometimes, is that we can see that when you cube a negative number, it stays negative, and that's where that negative infinity comes from. If we did this similar example with something like x squared, we would get that the limit is for negative infinity would also go to positive infinity. Make sure if you are going to write something like this that the quotation marks are important, as we're not really allowed to plug in infinity. For example 1b, we're actually going to have the exact same thing here. We're going to have the same horizontal asymptote on both sides. And that's true because it's a rational function, which you will see on the next page. So this limit is also going to be 1/3. And for sine, same thing. It goes out in the other direction the same way. As x approaches negative infinity, y is going to go back and forth, and this limit is going to be does not exist. The only one that's different is this first example. The other two have the same limit. All right. Now let's take a look at rational functions. When we're thinking about limits as x goes to infinity, we're going to be dealing with rational functions a lot. Something on the top, something on the bottom. And from pre-calculus, you should have dealt with rational functions before, and you should have talked about horizontal asymptotes of those functions. So let's review a very important result from pre-calculus. Given some rational function f of x, which is going to be p over q, p and q are polynomials, then we have three different cases for horizontal asymptote. If the degree of p is bigger than the degree of q, that's saying that the top is much bigger than the bottom, then there's going to be no horizontal asymptote. So in this first example, we have 3x squared plus 5x minus 4. We're talking about the degree, talking about that 2 and this imaginary 1 right there. So the degree of the top is 2. 2 is bigger than 1. So there is no horizontal asymptote. If the degree of p of x is smaller than the degree of q, that is, the top is smaller than the bottom, then there is a horizontal asymptote of y equals 0. So in this case, the degree here on the top is 2, the degree in the bottom is 3, 2 is less than 3, so we do have a horizontal asymptote of y equals 0. And finally, if the degree of the top is the same as the degree of the bottom, then we have that the horizontal asymptote is y equals c, where c is the ratio of the leading coefficients. So the leading coefficient on the top is 1, and the leading coefficient on the bottom is 3. So we have a horizontal asymptote of y equals 1/3. And if we go back to the previous pages, we can see that this is the horizontal asymptote that we came up with for this exact function, x over 3x minus 1, approaching 1/3. Now this all has to do with limits. This is now saying that the limit as x goes to infinity for this function f of x is going to be infinite because the top is much bigger than the bottom. There's no horizontal asymptote, which means that we're approaching infinity. In the second case, we have that this limit is 0 because of the horizontal asymptote y equals 0. This is the bottom is much bigger than the top. And then finally here we have that the limit as x goes to infinity of this function is 1/3, again, because of that horizontal asymptote. We are going to use those facts from the previous page throughout calculus, and we're going to be very quickly be able to say what the limit is as x approaches infinity or negative infinity. So for example, in this page, or this example, limit as x approaches negative infinity of 2x squared minus 4x plus 3 over 3x squared minus 7. We're going to be able to quickly say that the answer here is 2/3 because the degree is the same on the top and the bottom. So we look at the leading coefficients. If you're on an exam or trying to explain your answer, you could just say by properties of rational functions. This is something that you learned in pre-calculus, and you can use that for free without much explanation. Algebraically, we can think about this in a different way. We know that as x gets closer to negative infinity or positive infinity, doesn't really matter which one, that only the largest term on the top and the bottom is really going to make a difference. This is where those rules come from on the previous page. So it's also not incorrect to say, as x approaches negative infinity, this function, 2x squared minus 4x plus 3 over 3x squared minus 7 is going to be about the same thing as just 2x squared over 3x squared, which is the same thing as 2/3. That's kind of another way to think about this limit. Now we're going to show how to do this explicitly with algebra. And we're going to be using this trick for some other problems other than this that we can't easily say with this degree argument. So the idea here written on the top of the page is that we are going to divide both the numerator and the denominator by the largest power of x that goes into both the top and the bottom. In this case, x squared. So we're going to show our work very carefully, having the limit as x goes to negative infinity. We're going to rewrite the problem here. 2x squared minus 4x plus 3 over 3x squared minus 7. We are going to divide both the numerator and the denominator by x squared. Giving us a kind of gross-looking complex fraction. And then we are going to simplify both the top and the bottom by breaking that one fraction into three different fractions. So we're going to have 2x squared over x squared minus 4x over x squared plus 3 over x squared. And on the bottom, same sort of idea, two fractions, 3x squared over x squared minus 7 over x squared. And in each of those five fractions, or at least some of those five fractions, we can simplify very quickly, giving the limit as x approaches negative infinity. On the top, we have just a 2 minus 4 over x plus 3 over x squared. And on the bottom, 3 minus 7 over x squared, canceling out powers of x. The reason that we want to do that is now this limit we can break up into 5 separate limits. We can look at the limit of 2, the limit of negative 4 over x, the limit of 3 over x squared, the limit of 3, and the limit of negative 7 over x squared. And 3 of those limits all go to 0. This negative 4 over x, as x approaches negative infinity, goes to 0. You're going to have 4 over a really, really big number, which is basically 0. Same with this 3 over x squared. That goes to 0. And this 7 over x squared also goes to 0. And we're going to be left with limit as x goes to negative infinity of 2/3. And the limit of a constant is just a constant. So we showed how to do this problem in 3 different ways, going more difficult as we go down. The first way is we just know by properties of rational functions that this answer is going to be 2/3. Look at the degree of the top and the bottom. They're the same. Look at the ratio of leading coefficients. You could also say that, just kind of explaining the rule a little bit more, that as x gets really, really big, you only need to think about the dominating term in the top and the bottom, the largest term. And you could say that 2x squared minus 4x plus 3 over 3x squared minus 7 is about the same as 2x squared over 3x squared. Cancel out the x squareds, and that's just 2/3. But if you want to show it explicitly, you could do this trick where you're going to divide by that x squared that both the top and the bottom have in common. And this is a very careful way of doing this limit. And the reason we're introducing this is not to make busy work, but to show that we can do other problems that aren't necessarily rational functions that don't work with the previous page. And let's see one of those now. So we're going to do the same kind of trick, but this time we don't have a polynomial on the top. This is not a rational function, and that's a problem. So you can't necessarily say the degree of the top and the bottom. We're going to have to do kind of a trick of dividing by the biggest power on the top or the bottom. Before we do this, we need to do a little bit of algebra to kind of make this better. We're going to be trying to simplify that square root. So first we're going to look at something that is wrong. We're going to label this as wrong so you don't get confused. This is a mistake that a lot of students make. Doesn't make it okay. But that we want to write this as the square root of 2x cubed plus the square root of 4x. This would make this problem a lot easier. We could write this as 2x to the 3 halves, square root of 2x to the 3 halves, plus 2x to the 1 half. And we kind of think about this as a polynomial function more with rational exponents. But this is not okay, this equal sign right there. So we are not going to deal with that. We have to be a lot more careful with addition under the square roots. So we're going to mess with this square root carefully here. The square root of 2x cubed plus 4x. We are going to factor out the largest term, this x cubed, from both those terms. We're going to take out an x cubed out of the 2x cubed and the 4x. What I'm going to be left with is a 2 in the first term and a 4 over x squared in the second term. Might be kind of hard to go backwards, but if you multiply that x cubed in, I think it's very clear that we get 2x cubed plus 4x. Then we can take out that x cubed in the square root, and this would give us, we'd say, the square root of x cubed times the square root of 2 plus 4 over x squared, which we can write as x to the 3 halves times the square root of 2 plus 4x over x squared. And this is what we want, this x to the 3 halves. This is the biggest power that we're going to divide by. So let's take care of this limit now with this idea that we're going to divide by that x to the 3 halves in the top and the bottom. Now let's look at this limit. We'll rewrite the limit first. Square root of 2x cubed plus 4x over 3x minus 2. And we're going to rewrite that top using that square root thing we did at the beginning. We can write this as x to the 3 halves times the square root of 2 plus 4 over x squared all over 3x minus 2. And now we're going to do this thing. We're going to divide the top and the bottom by that x to the 3 halves. So So rewrite the top here and divide by x to the 3/2. And the bottom, we are also going to divide by x to the 3/2. Now it's very nice on the numerator, those x to the 3/2 cancel out. And we're going to be left with square root of 2 plus 4 over x squared on the top over 3x over x to the 3/2 minus 2 over x to the 3/2 on the bottom. We're thinking about the limit as x goes to infinity. This 4 over x squared goes to 0. This 3x over x to the 3/2 goes to 0. 2 over x to the 3/2 go to 0. We'll be left with square root of 2 over 0. Put that in quotes as we can't really divide by 0. But we know that if we have something like a finite number over 0, this means infinity, negative infinity, or does not exist. And in this case, since everything's positive, this is going to give us positive infinity as an answer. When we think about limits in chapter 1, if we have 1 over 0 or a finite number over 0, we have to check both the left and the right limits to make sure that we have infinity or negative infinity, or if they don't match up, does not exist. When we're thinking about limits as x approaches infinity, there's only one way that you can approach infinity, and that is coming from the left, getting bigger and bigger. So all we really have to think about is the sign, whether it's going to be infinity or negative infinity. We're not really going to have does not exist as an option when thinking about limits as x goes to infinity. All right, this is, just to be clear, this is like a rational function. This is kind of like a rational function where the degree of the top is 3/2 and the degree in the bottom is 1. And since 3/2 is greater than 1, we have no horizontal asymptote. That is true. There's nothing hitting going on, but technically this is not a rational function. We have to be a little more careful with the algebra. Let's look at one more example when we're thinking about limits as x goes to infinity. And this one is going to use the Squeeze theorem. So let's look at this limit. We're going to think about, first of all, that the fact that sine of x is not a very big thing. It is trapped in between 1 and negative 1. And if we think that sine is not a very big thing, it's in between 1 and negative 1, this limit is going to be a small thing over x, which means that this is going to be going to 0. But we can show it carefully with the Squeeze theorem. So here we go. Sine is in between negative 1 and 1, and we are going to divide everything by x so that we get sine of x over x. So we're going to have each of these parts divided by x, and we are going to take the limit of each part. So that's going to give me the limit as x approaches infinity of negative 1 over x. That's less than or equal to the limit as x approaches infinity of sine of x over x, which is less than or equal to the limit as x approaches infinity of 1 over x. Now, two of these limits are pretty quick to do. The negative 1 over x and 1 over x. This is going to give us 1 over infinity, negative 1 over infinity, which is basically 0. And over here, 1 over infinity, which is basically 0. It's 1 over a super huge number. You can test this by plugging it into a calculator. 1 over a billion will give you a very, very, very small number, getting closer and closer to 0. So here we have that the left-hand side is 0. Here's our limit that we're looking for. And the right-hand side is 0. And now we know that our answer is going to be greater than 0, less than 0. So by the squeeze theorem, this limit has to be 0. It is forced to be 0. You may be able to quickly think about that answer from the beginning. If you know that sine is not a very big thing, x goes to infinity, only the x is going to matter. Since it's on the denominator, it's going to be going to 0. We can carefully show it with the squeeze theorem. This is true of a lot of these problems that hopefully by the end of the semester and going into Calc 2, if that's where you need to go, you should be able to do a lot of these limits in your head very, very quickly. But it's important to be able to show why it's true and how it works, and doing that carefully with an algebraic trick or carefully with the squeeze theorem or something else. As that thinking and that thought process is going to be very important later on, although it may not be important for an individual problem in Calc 1, but that is why we are working on it. We will be using limits throughout the rest of the chapter. Limits are used for the rest of your calculus career. If you are not comfortable with limits, it is important to go back through Chapter 1 and review some of the fundamentals of limits before you even start looking at this section, and then making sure that you understand limits at infinity as well.